In today's video, we're going to look at projectile motion, which can actually be modeled by our standard form quadratic equation. So if you look at our projectile motion equation, it looks very similar to our ax squared plus bx plus c. The only difference is our constants now stand for something very specific. Our initial height, so the starting height in whatever motion we're going to analyze, is substituted in for s sub 0. Initial velocity is v sub 0, sort of like when you may have talked about things in experiments, your initial time is always 0. So that's how we are expressing that with the subscript of 0. And then we also have our acceleration due to gravity. So if you think about gravity, gravity actually pulls you down towards the center of the Earth. And so whenever we look at this constant, we're always going to have a negative number. Now, the actual acceleration due to gravity on Earth is negative 32 feet per second squared. But in our equation, to make this work, it's actually going to use 1/2 that value. So we would plug in, for most of our problems, we're going to stick with feet or feet per second squared. And so we'll use the value of negative 16 feet per second squared. Now, if we did do any problems using meters or meters per second squared, we would use the metric version of this. Again, full value of acceleration due to gravity would be negative 9.8 meters per second squared, and half of that would be negative 4.9 meters per second squared. But again, all the problems we're going to look at are going to use the imperial measurements. So A is equal to negative 16 feet per second squared. So let's check these out. And we're actually going to approach these by looking at the graphs of these values. And so specific points in our function or on our graph can actually give us information about that motion. So in example 1, the height of a rocket t seconds after being launched from a platform is given by the equation. So we need to figure out what's the maximum height the ball reaches and when does it occur. So we need a picture of this. So what I'm going to do is just plug in my function. Now it's written as h of t, and it really doesn't matter which variable we use when we're writing it down. But if we're going to plug this into Desmos, we do want to use x's, because we are putting this on an XY graph. So I'm actually going to type this in as y equals negative 16 x squared plus 88x plus 10. Now, as we're looking on the graph, it's definitely not centered very well. So we can play around with these a few different ways. We could actually use our zoom buttons on here if we wanted. But we also have the option of looking at this wrench, so our graph settings. And so what I'm going to do is I'm actually going to set my y value a lot higher than it is now. So I'm going to set this all the way up to 100 and see if that helps. So if you're worried about not being able to see part of your graph, you can always come in here and adjust your settings to get an appropriate size graph for what you're looking for. So that helps it better. It's still not quite big enough. So I'm actually going to go up to about 150. Excuse me. So again, let's change this to 150. And now we can see our entire graph. So if this is modeling a rocket that shot up into the air and then falls back down to the ground, well, if we want to find our maximum height, all we need to do is look for the very topmost point on our graph. And so with Desmos, that's as easy as just clicking on that point. So let's go ahead over here and we're going to go ahead and sketch our graph. And again, it's not going to be perfect, but I'm noticing on my Desmos graph, I've got these 4 points. So I want to approximate that when I draw it on my graph. So we don't start quite at the origin, we go very far up and then we come back down. And the topmost point that we found on our graph is at 2.75, 131. And so our question that says, what is the maximum height that the ball reaches and when does this occur? Well, if our height is shown by h of t, so this is our height, that's essentially our y value, so it's going to be our y coordinate on our vertex. So our maximum height is actually 131 feet, and it happens at 2.75 seconds. And that's really all we need to do to solve out a lot of these problems. Alrighty, let's look at our second example. So example number 2, an arrow is shot upward with a velocity of 64 feet per second squared. ignoring the height of the archer, how long after the arrow is released does it hit the ground? So first we need to actually write our equation. So our equation is going to be modeled after our h of t expression that we had up above. So we're going to have our acceleration due to gravity times t squared plus our initial velocity times t plus our initial height. And so this is giving us our information that we have upward velocity of 64 feet per second. So as soon as I see that, I know I can go ahead and use that negative 16 again, because it's using the same units of feet. So we have negative 16 t squared plus we have initial velocity of 64 feet per second, so 64 t. And it does say to ignore the height of the archer. So that means we have no initial height. We could plug in a 0 or just not plug it in. So let's see what this looks like on the graph. So negative 16 again. I'm actually going to start with y equals, and then negative 16 x squared instead of t squared, but it's still using one variable, plus 64 x. And so this graph definitely doesn't go quite as high. And you'll notice too, you don't have an extra point on here. We're only showing 3 points. So we have 2 x-intercepts, and then we have a vertex up the top. So let's sketch that. So again, we started basically at 0, 0. And the reason that happened is because you'll notice in the problem, it said ignoring the height of the archer. So in essence, it's saying, well, if we fired an arrow basically from the ground up, well, we don't have any initial height. We don't have any y-intercept to deal with. Okay, so this problem is asking how long after the arrow is released does it hit the ground? So in this case, we don't really need our our vertex. We need to know once this arc comes down, where does it hit on the x-intercept? So that point 4, 0 is what we're looking for. So that means the arrow went up and then it fell back to the ground. And if our x coordinates are giving us our time in seconds, that means it hits the ground at 4 seconds. Alrighty, next example. So example 3, a tennis ball is hit upward with a velocity of 48 feet per second. The height of the ball after t seconds is given by the equation h of t equals negative 16 t squared plus 48 t. So again, in this problem, we are ignoring the height of the tennis player. All we care about is our acceleration constant due to gravity and our initial speed. So first question is, again, ignoring the height of the tennis player, how long does it take for the ball to hit the ground? So same thing as before. So again, the only thing we're changing actually is our b value. So that now turns into 48 for initial speed. We've got even a smaller graph. So again, if you wanted to, you could zoom in. And again, I'm just using the scrolling wheel on my mouse. And I can drag that graph around as I need to see it. And so same sort of thing. We have the same kind of graph as example 2, where we're starting at the origin, the ball goes up, and then it comes back down. And so in part A, it wants to know, well, what's that x coordinate again, where it falls back down to the ground? So just clicking on Desmos, we find that's happening at the point 3, 0. So that means how many seconds? 3 seconds. But then question B says, what is the maximum height of the ball and when does it occur? So it does also want us to know what the vertex is. And again, just click on the graph at that point, and that gives you your info. So it hits at 1.5 for the x, 36 for the y. So that means, again, if h of t is our height, which value is going to be our maximum height? That's going to be max height at 36 feet, and that occurs at 1.5 seconds. And take a look at your graph, because this is going back to the properties that we've been using all along with parabolas. We know they're nice symmetric figures. And so if we're thinking, well, we have this evenly spaced between our two x-intercepts of 0 and 3, Well, halfway in between that should be our vertex, which is at the 1.5. So it still follows the same basic rules as the parabolas that we've looked at before. Alrighty, a few more examples. Let's see where we're at. Okay, so next example. Well, the gravity constant that we've been using is for Earth specifically. So gravity on Earth is considered negative 32 feet per second squared. And that should be an S in the denominator instead of an X. But that's okay. So why do we have these different values? Gravity is actually different on all these planets. So the scenario that we're going to use is exactly the same. If we drop an object from 100 feet, how long does it take to hit the ground? So for each one of these, we're going to want to write a new equation. And so basically, if we're given our constant due to gravity, don't forget we're doing half of that in front of our t squared. So for our Earth equation, our function, excuse me, let me go back to pen, h of t is going to be half of negative 32, which we already know is negative 16. And so that's our t squared, plus s sub 0, in other words, our initial height, which we're saying in every scenario, we're going to use 100 feet. So we can write that for Mars as well, that function. Well, half of negative 12, well, it's just negative 6. So negative 6t squared plus 100. And then on Jupiter, a much, much larger planet has a much larger constant of gravity. Mars is a lot smaller than Earth, so it has a smaller constant of gravity. And then half of 76, that's going to give us a negative 38. So before we actually graph these, what do you think each parabola, how do you think they're going to look different? Well, if we consider those A values, again, the larger the A value, the more that parabola is getting stretched. Every single one of them is negative, so we're still going to have an upside down parabola, which we'll have for any projectile motion problem. Things fall to the earth. They don't keep falling up. And so if we make that number, though, smaller versus bigger, that'll change how much we're actually stretching or shrinking that graph. Okay, so let's check out Earth. So y equals negative 16x squared plus 100. So I'm thinking for each one of these, we're probably going to, oops, and that should be a 100, not a 10. I'm going to have to adjust my graph again. So again, if I'm going to drop everything from a height of 100, what do you think I should change? Now, let's go ahead and change our y-axis. I'm actually going to bump it up a little bit higher than 100 just so I can see things easier. And so here's our graph. Again, we're not throwing it up. We're just kind of dropping it from 100 feet. So we're not going to be going up after that drop. Our rock is just going to start falling to the ground. For each one of these, if we're asked how long will it take to hit the ground, what point are we looking for? Looking for our x-intercept. So I just need to know this point down at the bottom. Alrighty. So for all three of these, our graph looks very similar. We start at a point and then we just drop. On this, our x-intercept is 2.50. So that means on Earth, it would take 2.5 seconds for that rock to drop. So for Mars, the only thing we need to change is our constant due to gravity, which is negative 6. And so if you'll notice, and let me put that one back in, our A value isn't as great, so our parabola isn't stretched as much. So it actually kind of pops out a little bit more from our axis. But same theory, we just need to know what the point is down at the bottom. And so this one's not exact, but keep in mind, if we're looking at real life problems, yeah, chances are our numbers aren't always going to come out really nice. So this one's approximately 4.082 seconds. Desmos is rounding off of it. And so what's the graph going to look like if we throw a negative 38 in front instead of the negative 6? Very skinny parabola, even skinnier than what we had in part A. So again, I probably could have spread these out a little bit more, but these are just sketches just to give us a rough idea of, which points we're talking about and just to give us a frame of reference. So our x-intercept on here is 1.6220. And so that means it's going to take 1.622 seconds. Again, the larger the planet, the bigger constant of gravity. In other words, things are pulled to the ground faster. So the biggest planet has the smallest amount of fall time. Alrighty. So 2 more examples on here. Might not be a bad idea to pause, maybe try these examples out on your own. Again, I'm just using the straight Desmos calculator, so you can see a site on there. It's just desmos.com/calculator. And try these out on your own, then come back in a few moments to see how you did. Alrighty, let's check out these last 2 examples. So example 5, the height of a baseball in feet, t seconds after it's hit, is modeled by the function. So we have all 3 values. So that means if you think about somebody hitting a baseball, again, in this case, they're taking that baseball player's height into account. So they're not starting right at the ground. Baseball player, when it hits the ball, it's definitely above the ground by however many feet. So our formula for this, again, we're back to -16 because we're still on Earth hitting that baseball. And our standard constant due to gravity is 1/2 of -32 feet per second squared. Okay, so plus 96x plus 3. So again, would probably want to adjust my graph. Again, I can either scroll or go into the settings. Either one works. But this one, again, as soon as I click on my parabola, you'll notice I have these 2 points that are kind of close together. It's a little hard to see, so actually I am going to go ahead and go into my settings. I probably don't need quite so much space on my x coordinates, so let's just go up to like maybe 7. Lucky 7. And we're not going up quite so high as 179 feet, so let's maybe just set it to 100. Ooh, it's actually going up higher than 100, isn't it? So let's go, what, maybe 150? And again, you can play around with these settings until you find something that works for you. Okay, again, very, very close in to that y-axis. Why do you think we have 3 as our y-intercept? Don't forget that y-intercept always comes from, oops, sorry, let me go back to drawing. Always comes from our constant at the end of a standard form equation. So we know we're going to start at 3. And they definitely kind of lobbed this ball if it went so high. Let's go ahead and pull all the points from the graph. So let's find our vertex and we'll find our x-intercept. So again, once you click on the graph, all you have to do is click on your points. So our vertex is at 3,147. Our x-intercept, and not the prettiest number, but that's okay, 6.0310. So initial velocity, initial height, well, that's just from the equation. So initial velocity, or v sub 0, is 96 feet per second. Again, that's not miles per hour, slightly different thing. So we could, if we wanted to, go through and convert that so we could get a better gauge of how fast that is. S sub 0, or initial height, is 3 feet. Again, that's our y-intercept. That's from where the ball was hit. Maximum height of the ball is just from the vertex. So 147 feet. And that happened at 3 seconds. And it hit the ground after, or at, we should use. So at 6.031 seconds. Okay, and then example 6, the bird drops a stick. So the bird's flying at 400 feet, which in the grand scheme of things, yeah, they're pretty high up, but think about how high geese might fly. So they're going to be pretty high up there. So first we have to write an equation. Keep in mind, it didn't mention anything about velocity, because if the bird just drops the stick, it's not tossing the stick, it's just letting go of it. So our equation h of t, and our negative 16 feet per second squared. And then our initial height is 400. So we don't need to worry about any initial velocity. So that means when I plug this into the equation, I'm expecting that I'm not going to be able to see the whole graph. Why not? If our initial height is 400, that means that's where we're starting at the top of our graph. So we need to bump up our y value very significantly. Let's actually put it up to 500. And there's our graph. So the bird drops the stick and it falls. And again, this graph is not looking at any type of directional velocity. So we are not taking any of that into account. Again, if you do study physics, you might talk about that in something called vectors. But we're not looking at that this year. We're just keeping it simple with our quadratic modeling. Okay, so we know our top point is going to be 400. That's when the bird dropped the stick. And then our x-intercept is at 5. So that means when will the stick hit the ground? At 5 seconds. Alrighty, as always, let me know if you have any questions about any of these problems. And if not, start working on your practice. See you later.